I would like to mention here that actually he is one of the father of the very famous matrix product space. Actually, he was contributing to engineer in the 90s, so much before of the quantum information boom. So today we will talk about new lattice gauge theories from quantum computation.
Okay, thank you. Good afternoon, everybody. So it's my pleasure to be here in Singapore. It's my first time. And I will talk about this title, which is relating lattice gauge theories, which are new, and they come from quantum computation. I will tell you what is... With this topic, I want to highlight that how quantum computation is so fruitful that it can give rise to models beyond the area in which it originated. And this new lattice gauge theory, they produce new types of gauge theory, different from the theory that appear from the QCD field in which they were proposed by Wilson and previously by Beckner. So before that, I would like to thank the Center for Quantum Technology's invitation to visit, especially Professor Blatko and Pedral and Professor Luigi Amicu. And also, I want to thank Evan for her very nice and helpful logistics. So, let me show my sponsor, because I must. And actually, in Madrid, we also care about quantum technologies, like this center. And there is a consortium called Quantum Information Technologies Madrid, which in the acronym is called QUIMAT. So we would like, well, we can share this interest on quantum technologies. So this is the structure of our consortium. So this is the abstract that I handed over the invitation. So what is the underlying topic of my talk? So the idea is to relate, this relationship between quantum computation and new lattice gauge theory comes from the fact that topological codes are very much related to fault-tolerant quantum computation. So much that you can identify them. Actually, to be more precise, you can say that fault-tolerant quantum computation is realized in an effective and in a feasible way by means of topological codes. It does not mean it is the unique way, but at least it is one possibility that works at the level of fault-tolerant quantum computation. So now topological ideas, they appear very often in condensed matter, strongly correlated system quantum information, topological quantum information. Many people believe that, well, these topological ideas are beautiful. Here, with this relationship, what I want to highlight and stress is that what I do care is not about beautiful. It is about useful. They are useful. I don't care whether they are beautiful or not. They are, of course, you see, these are very nice. But the point is that they are useful. And the usefulness will be measured by a figure of merit, which is the error threshold. And if this error threshold is much better than a standard, by a standard I mean non-topological codes, by a standard fault-tolerant quantum computation, then it is useful, very useful. And this is the difference between a standard fault-tolerant quantum computation and that based on topological codes. So this is a brief outline of my talk. I will mention briefly, just to framework, the quest for a quantum computer. And I will choose the option of using externally protected quantum computer, which is equivalent, by externally protected, you will see, it is, by definition, it is equivalent to fault-tolerant quantum computation. Then I will focus on a type of topological codes that we call topological color code, because they have nice features, more enhanced computational capability. And then the relationship with lattice gauge theory they will appear when doing the error correction analysis based on the classical information that you obtain when you do this error analysis. And this error analysis can be recast in the form of statistical classical models. And in fact, for these topological color codes, when you do a complete error analysis, you see that everything can be recast in the form of a lattice grid theory that is new and we call tricolor because of this color, which you will see. Then I will finish showing simulation, numerical simulation to compute the threshold and see that this threshold is much better than in the standard scenario. And actually, it is better than the threshold obtained with the original topological code, which is the Kita F code. And this is a very remarkable result. I will finish with that. So let me thank my collaborators, Hector Bombin from Perimeter Institute, Helmut Katzgraber, University of Texas A&M and ETH Zurich, and Ruben Andries, ETH Zurich, Switzerland. So the quest, let us remind what is the quest for a quantum computer. For me, this is a challenge for new physics. So I believe that in building a real quantum computer that will demand new physics, new state of matter. It will not be just something about engineering, some circuitry, and no, I don't believe that. I think that it will demand some new quantum state of matter. One candidate, the one that it is underlying this talk, is based in the concept of topological order in topological quantum matter. So just to give you an idea of the type of computer that you can consider according to their protection against decoherence, against errors, unavoidable errors. Well, you may start with a bare quantum computer, in which the one in which there is no error protection is simply the error-free model, the original one. Then you can try to battle these errors when they appear by means of external methods, by acting externally on your computer in order to detect and correct the errors and keep going, keep working. And eventually, in a higher level of sophistication would be the internally protected quantum computer. It's a computer that with internal physical means, it is able to correct the errors itself. So this is the dream, following these rows. And today I will focus on the second level. So fault-tolerant quantum computation is equivalent to this externally protected quantum computer. Today I will not talk about this, which is a dream, and there are partial results. But this scenario is what I want to show you is the topological codes offers you an efficient and feasible way to solve this problem. This other problem is still open. And this is a reason why still we don't have a quantum computer scalable. Okay, the bare quantum computer has already produced, in my opinion, new physics. Even though we have not produced the scalable quantum computer, still there is new physics behind, and for me this is pretty clear, and well, it goes back to the proposal with ion traps made by Ignacio Cirac and Peter Soller, and with string arrays in one dimension, or with micro tramps in 2 dimensions, and continuing with cavity QED, or later with optical lattices with the mode superfluid transition, and the mode is a quantum state which is amenable for quantum computations. And you can go on. I mean, the story has continued with making a new proposal about possible platforms to realize this quantum computer with circuitry QED and more things with quantum dots, solid state, well, you name it. They are optic-based quantum computer. There are many proposals. Still, we have not fulfilled this three level story that I told you in the beginning. But as I said, even there are proposals using dissipation to drive quantum computation. So the variety is huge. Now, nevertheless, this accounts for this type of quantum computation in which you don't have a fully mechanism to protect from the error, from the external errors. But it is known, there are theoretical studies in the 90s that tells you that it is possible to have a externally protected quantum computer by means of the notion of quantum error correction and the notion of fault-tolerant quantum computation, which the notion of quantum error correction, it is the picture in this schematics diagram, in which the idea is that you have an emitter and a receiver, and you want to transmit a quantum state phi along a noisy channel, and for that you have to protect, to encode it with quantum gates, and then send it through the channel. And in the intermediate state, you use auxiliary systems, qubit, in order to detect first where an error has occurred and correct by means of unitaries to recover from error and eventually decode, and you get at the end of the other side of the channel, you end with the initial quantum state with a very, very high probability. So these are the main features of quantum error correction. And experimentally, there is recently a nice paper in which this repetition code with the three qubits, it has been realized experimentally in Innsbruck in the group of Professor Blatt, Rainer Blatt, in this publication by Sindler and company. But this publication is for 3 qubits. So still, we are far from qubits, from codes that can protect from arbitrary errors. So this is the scenario of quantum error correction. Fault tolerance is when everything can fail. I mean, everything means not only there is a noisy channel, but also the operation that you use to encode and the operation that you use to measure and detect the error, they are also faulty. They are also prone to errors. So you have to correct these errors. And so in the process of correcting errors, you can introduce new errors. So the error correction is really a dynamic process. It's not static as in this quantum error scenario. And this dynamic of the error correction is called fault tolerance. Now, the success of fault-tolerant quantum computation is the threshold theorem that tells you that if there is an error rate for either a qubit error rate or measurement error rate or gate error rate, whatever, that error rate tells you what is the external noise that can be supported by the quantum computer. And if you are below that threshold, you are living like in an oasis or in a very nice place like Singapore, in which you can do then long-term quantum computation with arbitrary precision, and everything works well. But if you surpass this threshold, then you enter in a disorder situation in which when you try to correct errors, there are more errors coming in, and you do not have time in order to correct them in enough time so that to reverse the situation and make it work and continues. You cannot in that case, and then everything explodes and you cannot work here, right? So incidentally, you see that this is an ordered place, this is a disordered place. So this looks like physically, I mean, this is from a quantum information perspective, but physically what is underlying here is a phase transition from an ordered phase to a disordered phase. And you will see that in the models that I will mention, there are these phases, ordered versus disordered. And in the case of the gauge theories, they will correspond to a Higgs phase, and this will correspond to a deconfined phase. So the good news is that fault-tolerant quantum computation is possible. The bad news is that the threshold is very small. So this threshold, this PC or epsilon naught, is typically of the order of 10 to the minus 5 or 10 to the minus 6. It means that, for instance, in terms of gates operation, you need to operate perfectly 1 million gates before an error happens. And this, nobody has been able to succeed in doing such a job yet. So even though theoretically fault-tolerant quantum computation is possible, in practice with these figures, you see that it is not feasible, it is not efficient. So the idea is that so far a topology has not entered, has not come in. When you use topology, you can improve this very, very much. And this is the reason why I told you before, fault-tolerant quantum computation is realized by means of topological codes. This is the circuitry that this group in Innsbruck used, using ion traps based on calcium ions in order to fulfill this 3-qubit error correction, which is not complete, but this is a proof of principle, and it has worked very nicely. Here, this group is very nice setup because the ancillas, in the previous transparency, you see here that there are these ancillas in addition to these 3 qubits that we use to encode the qubit, the physical qubit into the logical qubit. But here, they are very smart, and they use part of the system as ancilla, yes and no, depending on along the flow of the computation. So they handle they manage to do everything with 3 qubits, even though they are using 2 of them, sometimes as an ancilla, sometimes as part of the system. So they are very clever, very smart, but nevertheless, they have not been able to do this for a complete quantum error correction. Still, this is open. Now, for fault-tolerant quantum computation, what do we need? We need first fault-tolerant measurements for error recovery, and second, we need fault-tolerant quantum gates because we want quantum processing to be fault-tolerant. Now, as I told you, the idea of quantum error correction is that, in principle, it is static, but the moment that you consider that errors may come into the error correction itself, the system becomes dynamical, and because there is propagation of errors. Propagation of errors means that, well, this is an error. Means that if you have an error occurring in one part of your system, applying gate, it can propagate. For instance, here you have one error in this line, in the measurement line. It can, after this C0, it can propagate here in this qubit, and if you apply another C0, it can propagate here, and so on and so forth. So with one error, you can end up with many errors afterwards. So this is the idea. So the crucial idea here is that one should use an strategy in order to prevent this propagation of error. And this strategy is called a transversal property. A transversal property in the application of gates. It means that if you have your logical or code qubits here and here, it means that you apply transversally, means that you apply by tensor product your gate. So if it is a unary gate, tensor product means that you apply by tensor product transversally in all the qubits. If the gate is 2-qubit gate, you apply it by tensor product transversally in all the qubits from one code to another code. So it's clear, it leaps to the eye. So here, this is a bad version for measuring a syndrome, and this is a transversal measurement. Now, what I tell you is that with this type of construction, what you can do is to avoid this propagation of errors. I mean, to keep control, to keep that error propagation under control. So when you do that, and you combine this with a concatenation of code, so it means that, for instance, in this 3-qubit repetition code, 1 qubit, 2 qubit, 3 qubit. Now, at this level, one of the qubits, you see that inside there is another level of encoding by means of 3, and each one is encoded into another 3. It's like a Russian doll. Then, combining these two strategies, you can prove the error threshold theorem, which here is stated in technical words, but it's the same thing as I showed you in the picture before. And the problem with this is that the numbers that you obtain with this strategy, they are very bad. From the point of view of a lattice, this coding is like having a binary tree, some kind of binary tree. So you mean 0 level, then first level of concatenation. So here goes, and so. Right. So this is what we are doing with the standard non-topological quantum coding. Now, the topological case, what we will do is we will substitute that with a lattice. It could be of this way, a square. and we will place qubits here. And the good thing will be is that we will do the basic components of this coding, they will be local. While this coding is non-local. So this will be less efficient, while this will be efficient. Okay, so what you get after doing this construction is a set of gates that it is fault tolerant, is tolerant to errors. This is an example of discrete set of gates by means of the Hadamard, the square root of k. K is square root of k is this. It's a unary gate, and this is the CNOT. So this is universal, and moreover, it is fault tolerant, and it can be implemented transversally. So it's a good choice. There are other choices. Like the one below, but this involves the Toffoli gate. So you remove the square root here, but you pay the price of making 3 qubits. Now, so far there is no topology whatsoever. Here is I tell you what happens when you consider a topological coding of these things. The idea is that the outcome of the new construction with the topological quantum computer is that error correction is related to a random lattice gauge theory. Now, the phase diagram of that theory will give you a line in which you can distinguish the ordered phase in which quantum computation is possible from the disordered phase in which it is not possible. And this is called the Nishimori line. And the observables to detect whether it is ordered or not, they will be Wilson loop observables, and you can detect them because of the area law versus perimeter law that they exhibit. So this is the phase diagram. This is P. This is the parameter. This is P naught. This is the threshold that I mentioned before. This is an auxiliary temperature. So this line here, this dashed line, is the line in which quantum computation may take place in this phase, in the Higgs phase, order phase, and it may not take place beyond that because it is disorder. I am advancing result. Now, let me briefly introduce the idea of topological codes. Toric codes, topological codes, the idea was introduced by Kitaev in his famous papers in 1997. And the idea is that the stabilizer generators for the coding in the case of standard non-topological codes, they are non-local, as I said here. And this is a big problem from the theoretical point of view and also experimentally. So toric codes are a way to use topology in such a way that one can use this topology to protect to encode and also to protect our information. So what is topology? Remember this famous sentence by John Kelly: a topologist is one who doesn't know the difference between a donut and a cup of coffee, right? You may see a topologist is a stupid guy because you can clearly see the difference between a cup of coffee and a donut. Even a baby knows the difference between a soda and a donut. So how can you do something with, becoming a stupid guy? Well, topology knows a lot about entanglement and surface theory. Let me illustrate this with this paradox, toroidal. So here you have two torus. This is one torus linked to a two torus. This is one hole, another hole, linked. And you may ask whether the topologist, one person, like I told you before, whether he can continuously deform this linked two tori into this situation in which one of the tori is linked only once and the other one is unlinked. Right? This is one. So you may think, is this possible or not? Because this is the situation that we have here. We deform continuously and go from here to there or from here to there. And this is topology. Continuous deformation without tearing apart your surface or your system. So is this possible? Do you think it's possible? No, it's not possible. Unlikely. It's fuzzy logic. It would be possible or not possible. But well, you could have guessed that it is possible, because if it is a paradox, it is possible. How? Well, look at this situation. You deform this arm here into this position, and now you start deforming from this side in this other position. You continue deforming here down, and finally you get the final situation. So you can see that following the rationale of a topologist, you can see that from his ignorance, that ignorance can be a source of knowledge, right? Because you can do something which is non-trivial, being that ignorance. Now, what this tells you is that there are global properties, that they do not change under small local deformation, continuous deformation. So, and this is the idea that Kitaev had, but instead of working in real space, in coordination space like here, working in the space of quantum states, in Hilbert space. So the idea of topological codes is to bring these notions into the area of the quantum Hilbert space of the states, and to implement this deformation, this type of encoding, the encoding by means of global properties of your surface, of your lattice, right? So that if you put your logical information into the global properties of your lattice, then if an error occurs such that, and this is an assumption, that error is local, that local error will amount to doing this kind of continuous deformation. And eventually the global structure will not change. So your logical information will not suffer from damage if the errors are local with respect to your configuration of qubits, physical qubits. So this is the basic principle. Now, once said that, let me tell you that we should be open for other ways to battle decoherence. I mean, I'm not saying that this is the only way, so one has to be imaginative. One has to be imaginative in order to look for the alternative against, for battling against decoherence. This is just a word of caution. Now, what are topological color codes? How do we implement these ideas in a specific situation and practical way? Well, this is a situation in which I have a surface, and these grains are qubits arranged in such a way that the stabilizers of our coding system will be local. So local here means a few qubits with respect to the complete set of the qubits of your system. And the logical operators are the qubits will be related to global properties. Global means that it sees something non-trivial, this whole, this genus here. So they will be related to other operators which are non-local. These are called string operators. So if a local error occurs, like I said before, in this case it happens in the form of an open chain, this red, then the encoded information will be related to a string of operators that will wind around a global feature, a global property of your lattice, like here. And if an error occurs locally, like here, this red means a string of errors appearing locally, then that would amount to doing this, a deformation of your logical information, and this deformation, which is continuous, has not changed the global properties of your system, and then the information would be safely stored. So this is the idea, without getting into mathematical details about homology groups. This is the idea behind storing information topologically. So, again, in order to do fault-tolerant quantum computation, it is desirable to have the transversality property that I mentioned before at the level of the stabilizer formalism. Remember, the stabilizer formalism is formalism in which the code space is made for all these states that are stabilized by the stabilizer group, which is a subgroup of the Pauli group of operators, an abelian subgroup of that, and it is stabilized trivially with eigenvalue 1. Okay, so color codes is a way to make compatible the topology with the transversality property. Topology was introduced by key-type, but key-type codes, they lack the property of transversality. And combining both, making them accessible, it's what brings you about this notion of color codes. So eventually, what you will have is a computer seen as a stack of layers. In each layer, you will have a qubit stored logically, made of several physical qubits. From the point of view of condensed matter, this will be a topological order system. From the point of view of quantum information, you will use that to store information, and you will address with lasers, standard lasers, this system with one layer or two layers, you want, depending on whether you want to implement a 1 qubit gate or 2 qubit gates. So as I said before, originally the first proposal for this topological code is the key-type code, which is made of these arrays of, this is an example of an array of a lattice arrays, a square lattice with qubits on the edges, and the stabilizers, the stabilizer operator, they are defined on the plaquettes or on the edges. On the plaquette, they add by means of this string of X operator, Pauli operator, 1, 2, 3, 4 around the face, or in each vertex there will be also 4 operator, 1, 2, 3, 4 around the vertex, around the face, around the vectors. Here you can see the same thing, and I stress that qubits live on the edges. Errors appear in the form of chains. So here you see this. Here an error occurs, and it is detected by the violation of this vertex stabilizer operator. And the same of here, they come into pairs, right? And this is a string of errors, and if I have to detect this string and apply operators on it in order to remove the errors. So the stabilizer will detect tails of chains. So what I will see is only the end point, not the real chain of errors. This is because there is this redundancy in the topological coding. So what I will have to do is to compute the path of which is most likely. So this is the real path, and I have to compute this. What is the probability of finding this path in order to detect and correct the errors? Now, in doing that, potentially it introduces new, trivial loops. So suppose that I have this green path for the errors, the real one, and what I do is I correct, because I have to make a guess. I only see the endpoints, I don't see the real red string, so I do something that I recover from errors along the red path, and this is legal. This is legal because the difference, I mean, the difference between this red and this green and this red path, the real one and my guess, in order to do error correction, the difference is something that is homologically trivial, topologically trivial. What it amounts is to a chain. It changes the shape of the loop where I have encoded the information, but does not alter the coded information. So this is a smooth deformation that I mentioned before. This is like when we were transforming the tori in the real space, but here it is done at the level of the quantum Hilbert space. Now, the topological color codes is a new topological code in which the lattice is different. It is not the square lattice. It is based on what we call color simplices, color lattices, like the hexagonal lattices. The qubits will be placed on the vertices, not on the edges, and the errors, the change of errors, they may form the standard pattern of strings, but also they may have also this string net configuration. It may be a one violation of this plaquette operator, and also another plaquette in such a way that we have a branching of change, error chain. I will show you in more details. So why do we do this? Is because in this way we can bring about the property of transversality, which is good to do fault-tolerant quantum computation. So this is a comparison between toric code and topological color code. The stabilizers are substituted by always plaquette. Here they are plaquettes and vertices. The tails, they are strings, but here it could be something more, richer, like this string net, because this is a branching point. And and these are the tails associated to that branching. So this is an example, a generic example of a color lattice. Here you see the basic ingredient is a lattice in which each vertex is trivalent. So coordination 3, not 4 like in the square lattice. Now, the lattice must be colorable by phases. So here you have a phase of green color, and it is surrounded by phases of different colors, say red or blue, and likewise for the other phases. Equivalently, you may see that each vertex is linked by edges of 3 different colors. So it is also a lattice that it is 3 colorable by edges, not only by faces, equivalently by links, by edges. Why do we do this? Is in order to preserve transversality under topology. Here, so how do we construct my system, my quantum system? I take my lattice with coordination 3, and I place a qubit in every vertex, not edge as in the Kita-F model. And the stabilizer, they always will be plaquette operators, either of Pauli type X or Pauli type Z. So here there will be S1, S2, S3, S4, 5, 6 around here, and the same for the Z. So XZ plays the role of a flavor. So I can have errors corresponding to violation of stabilizer condition on plaquettes of equal color, like blue and blue, along this string of blue operators. Or more generally, I can have even a situation in which I have this branching of 3 colors, like here. So mathematically, this gives rise to a new notion of homology, we call color homology, because homology usually allows you to deform this into this, but with these color codes, we can even deform by branching colors in such a way that at each branching point, you have the 3 colors meeting. It's like the 3 colors giving a white color. This is the situation. So this is the standard topological situation. This is the new one we have introduced. And this corresponds to equivalence between a string of Pauli operators. Now, how many qubits can we store in this system? Well, the situation is different from the Kita-F. The constraints are different, and if we take into account the constraint, we see that the number of qubits that we can encode, the logical qubits, is twice the number of the Kita-F code, and actually it's twice the Bethe number. The Bethe number is a topological invariant of your surface, of your lattice embedded into a surface, and it is related to the Euler characteristics by means of 4 minus 2 times x, and there is so we gain more storing capabilities with color codes, twice as much as with the Kita-F code. And I must tell you that we do this without increasing the number of physical qubits. We can show that. So we are not cheating. I mean, it's something that you gain more paying nothing else. We can construct a string operator in such a way that when they cross, they anti-commute, and this allows us to encode logical operator, non-trivial operator, in this loop around the holes of these surfaces. And what we have is that with a torus, with the ordinary colors, the color code gives you 4 qubits encoded, while the Kita-F code, it gives you 2. The reason is because we have this color degree of freedom, which is on the lattice. It's in the interaction. It's not in the qubits. I mean, the qubits are always 2-level system here, 2-level system here. You here see 2 colors, red and blue. You don't see the green because the green is redundant. I mean, once you fix the red and the green, the red one can be deduced. So this is why we have 2 colors here. If we have more complicated situation with other higher genus surfaces, you can do the construction as well. Now, of course, experimentally, it's very difficult that one day you will construct something like this. So you have to find something more practical, and these are called planar codes. So planar is something that you can put on a plane, and then the non-trivial topology appears in the form of holes. That's something that gives you. And more particularly and more interestingly, it can be related to the color of the edges, which correspond to the to the condition of the stabilizer formalism. So the way to do this is you take a sphere with your color code embedded, you remove one qubit along with the links meeting in that qubit and the faces meeting in that qubit. You remove all this and you open, like here, open, you cut it, you open, and you flat it onto the plane, and what you obtain is this triangle planar code. And what you see inside, if you look inside, what you will see is the trivalent lattice, color lattice, with coordination number 3 and the 3 colors on the right here. And this is the minimal example of a qubit, of a planar color code with 7 qubits. And with this, I can prove, I will skip it, I can prove that this, you can implement the set of gates of the Clifford set of gates, the Clifford group. So you can do things like topological distillation, topological dense coding, topological distillation, topological teleportation, everything that you can do with the Clifford group. This can be generalized to 3 dimensions, and these are expressions for the encoding of the logical states. This is something technical. This is an example of a color code by means of the standard honeycomb lattice, the hexagonal lattice, and here you see the errors that appear in the normal way by means of the strings, and these are the new type of errors corresponding to this three-point violation of this condition, stabilizer condition, by means of this string net. Incidentally, these strings, this endpoint of this string, they carry anion particles. Okay, so how do we do the error correction here? Well, in doing that, what we will see is that we will obtain new statistical models with randomness. And how does happen? This is again the phase diagram we will see, is because in order to perform the error correction, what we have to do is to measure. We have to measure the syndromes of the errors, and from that information we must have what is the most likely path in order to do error recovery given that pattern of syndromes, errors. Well, when you do the analysis of the probability of finding one chain of real errors as opposed to one deformation, one local deformation given by this E prime, so they belong to the same homology class. It doesn't matter whether I correct through this red path or through this deformed path by means of this closed loop, because it does not alter my properties of my code. Then what I can see is that probability, which is a counting that one does, that can be recasted in form of a Boltzmann weight, a certain probability. And this probability can be computed with an associated partition function for the fluctuation of these loops, these E prime loops that appear as deformation of the real error loops that happen into our system. And this is the form of an Ising model of classical variables, sigma, spin variables, with couplings that are random in the sign. So the sign of the interaction could be positive or negative, depending on whether, with a probability p, this is 1 minus p, depending on this qubit error rate that I have from the outside world. So I can show that this probability of finding a deformation of my error chain, my guess, can be computed by means of this statistical mechanical model. I will show you later more details about this. So this is what is called a random bond Ising model, that I can compute the phase diagram of this, and then I can compute what is the critical value, the error threshold for this topological code. This is what happens with the key type code. What you have is a random bond Ising model. This one here. So if you remove the fluctuation in the sign, what you obtain is the normal Ising model. But if you have this fluctuation, then you have a random bond Ising model. It's a model with bonds that fluctuate according to the errors, external errors. Now, what happens with the color codes? With the color code, we have the situation is different, because when I have one violation in one qubit, it affects an error in this qubit can be detected by three surrounding plaquettes. So in this mapping, in this statistical mapping, I place one classical spin by each stabilizer. Stabilizer here is related to a phase, another phase, another phase. And this qubit, which is the physical qubit, gives you the interaction pattern between these classical spins corresponding to the plus-minus sign of the violation of the stabilizer. So altogether, what we have here is a three-body classical interaction. So it's a three-body classical spin system with couplings that depends, the sign of the couplings will depend on these triangular plaquettes, which lives in the dual lattice. So this is, the situation now is a new type of random, not bond, but random triangular Ising model with three-body interaction that you have to find out the phase diagram. In this case, in the case of the Kitaev code, Kitaev and Preskill, they didn't have to do any numerical simulation because this was done by other people before, so they obtained the number, the threshold from other people. In our case, we have to do the analysis, the numerical analysis with Monte Carlo and see what happens with the error, with the qubit error rate, with the threshold. And the big question is, will it be smaller than the Kitaev? If it is much, much smaller, then it is useless. But if it is something of the same order of magnitude, then we are happy because we have more quantum capabilities, we can do more quantum gates at the price of, well, it will depend, the price will depend of the error threshold of this model. Okay, what is the numerical analysis? It's here. Again, here I have to put the P, the degree of disorder, my external noise, and here I have to put the temperature of this statistical mechanical model. And these are numerical values, and this corresponds to the ordered phase, the disordered phase, and this is the Nishimura line that I mentioned before, is the line that in which the real quantum computation is mapped onto. Well, these are the type of lattices. Now everything is encoded into classical statistical mechanical models because of this statistical mapping to the syndromes that could be plus or minus. And by doing this is the same as I said before, by doing the analysis of the finite size scaling analysis of this system, of this statistical mechanical model with randomness, I can detect numerically the critical point by doing a plot of the correlation function versus the temperature. If this for different lengths of the system, if there is no crossing for different lengths, then there is no, I mean, the critical point is 0. Then we have nothing. But the standard situation will be in such a way that when I change the size of the system, there will be a common point in which things cross, and this will detect the critical temperature for a given disorder P. So when I do this for zero disorder, I obtain the triangular lattice with this three-body interaction, and this is the Buster-Boo model that can be solved exactly. It's an integrable model, and the Ising model, well, it corresponds to these critical exponents, and this we have checked numerically, right? So the phase diagram for this point, for zero disorder, we can reconstruct it numerically, and this is something confident that we are doing good numerics. Now, the next step, and the same goes with other exponents. The next step now is to increase the disorder. So suppose that we increase the disorder to 0.02. So it's not 0, and then again by scaling the length of increasing the length of the system, I can see a point in which it crosses. Right? This is the length of the system, and it crosses at a certain value of t. This value of t is different from this one. It's smaller. So what happens is that instead of being here as zero disorder, I am here with a little mod of disorder. I repeat this for increasing the disorder 2 units, and now I am here. I continue, I am here, I continue increasing the disorder, then I am approaching the Nishimura line in which I want to hit that line, because that would be the threshold. And you see, we are now I hit it, essentially 0.109. Still I have crossing, but clearly if I go beyond, I lose crossing. So here clearly it is seen that I lose closing if I go beyond certain point. So what do we have? What we have is that we have mapped out the phase diagram of this statistical mechanical model with randomness in such a way that this region is an ordered ferromagnet region, and this is a paramagnetic disordered region, and this point is the critical point that gives me the threshold. And very, very nicely, it gives us a value which is the same as in the key-type code. 0.109. Actually, we have measured with even better than it was measured for the random Von-Ising model. So this is very nice because what we get is the same threshold as in the key-type model. So we have not lost any efficiency of the model, of the computational model, and we have gained. Remember, we have gained more quantum gate that we can implement because we can do the Clifford group set of gates instead of just the normal gates S and Z. Now, interestingly, this value, this threshold is it corresponds to the Hassing bound. So we hit this, and this is a mystery. Why it corresponds to the Hassing bound? I mean, it's a bound, but we saturate the bound, and we don't know the reason for that. It's a mystery. Okay, so in the tricolor lattice gauge theory, as I'm running out of time, what we do is, in addition to qubit error, we take into account measurement errors. So what we do is we have to make one run of error syndrome measurement for one layer and repeat the thing another layer and another layer. So effectively, it's like introducing a time duration. So what happens is that instead of having a statistical mechanical model, normal model, what we have is that in order to battle against measurement errors, we have to make a series of measurement for several layers, and the model becomes a statistical mechanical model in one more dimension. So it is a three-dimensional model. And actually, it can be shown that there is a lattice gauge theory associated to this structure. There is a structure of this tricolor lattice gauge theory. There is a layer with hexagon, there is another layer with hexagon, and in between two layers of hexagon, there is a layer with triangles. And the interaction is, instead of having this three-body interaction, what we have is a five-body interaction corresponding to these three-layer interactions. This double tetrahedron, 1, 2, and this 3, 5. So these are classical spins, and these other correspond to the spins around these hexagons. And these variables are, again, quenched variables with probability P and Q, depending on whether it is qubit or measurement errors. Okay, what is a lattice gauge theory? Well, lattice gauge theory, they originated in the non-perturbative studies of QCD. And let me mention that in this area, a lattice gauge theory is an artifact. It's an artifact. It means that the real theory is defined in the continuous, but as you cannot do non-perturbative calculation, you have to put things into a lattice, make calculation there, and then take the continuum limit. That's what Wilson taught us. Now, the thing is that at the level, if you compare what is a gauge theory is the opposite of a global symmetry theory. So the Ising model, the standard Ising model with classical variables, it has this two-body structure. It is invariant under a global flip of a spin. You flip all the spins, the Hamiltonian function does not change the energy. However, lattice gauge theory, they are made out of plaquette interaction around plaquettes, classical interaction. Now, with this plaquette interaction, you can show that if you flip spins around a vertex, this spin, this spin, this spin, this spin, but not the rest, you can show that this Hamiltonian function, energy function, does not change. So the notion of a gauge theory is an implementation of local symmetries. So you have more symmetry than with a global symmetry. And you can see that, well, when you go into the continuum, you can recover, for the case of group U1, the quantum electrodynamics, or for SU3, you can, or SU2, you can connect to electroweak or QCD, etc. But again, at the end, you have to send the spacing, the lattice spacing to 0. The nice thing about here is that this model that we have found, they are legitimate models without taking the continuum limit. Taking the continuum limit is a nightmare for numerical simulation. But here we don't need to do that. We have to do the thermodynamic limit, but not the continuous limit. And again, you can detect the ordered phase, quantum computation, and the non-ordered phase by means of non-local operators, which are called Wilson loops. Okay, this is the tricolor lattice gauge theory. It is a theory. It comes about making the history of error syndrome measurements in our color code, and then this story can be recast in the form of a statistical mechanical model that gives you the probability of finding the most probable path for recovering from errors. And the thing is that if I make, in the previous Hamiltonian, in this Hamiltonian of here, if I make a local change involving these 6 spins of this hexagon plus the above and below spins, above and below with respect to the center of this plaquette, all together, if I do that local spin flip, then this Hamiltonian, I can show you, it does not change. So this is a new type of lattice gauge theory because it does not involve plaquette operation, vertex operation around the plaquette. It involves something corresponding to the volume. And that's something that was, we have not seen something like that before in lattice gauge theories. And actually, the gauge group, we can identify it by studying the excitation that comes into the form of 3 fluxes, color fluxes. This is why we call it tricolor, because fluxes are 3 colors. And it corresponds to a group which is set 2 cross set 2. Okay. Now I am finishing. I have to do the simulation of this in order to obtain the threshold. Now, I have to do it measuring the correct observables, which are Wilson loop, non-local observables. If I do, what happens is that the same analysis as I did before in the 3-body interaction Ising model, we see immediately that there's something new going on. And this new thing going on is the fact that the phase transition before it was second order. And here in this lattice gauge theory, we have detected that it is first order. If we study the population of this Wilson loop, we'll see, with respect to its length, we see that there are 2 populations. So there is a mixture of 2 populations. This is a clear signature of a coexistence of 2 phases. And this is a first order phase transition. So in this lattice gauge theory, the phase transition is first order, not second order as in the standard global Ising model. So why is this important? Because then you have to redesign the observable in order to detect that critical point. And this is the observable. We call it skewness. And by doing this, when doing this analysis, we have to again plot P, the disorder in the qubit and in the measurement. We put them equal, and we start in the zero error, in the 0 noise, and we start increasing the noise in the measurement and in the qubit errors, and we do the same time of analysis, finite size scale analysis, until we hit the Nishimori line, where this is the situation in which you distinguish quantum computation, fault-tolerant versus non-fault-tolerant quantum computation. What we find is something very remarkable, because the critical point now is 0.045. So it's less than before. So this is 4.5%. Before it was 11%. This is natural to have less threshold, a lower threshold. Why? Because we have more type of errors. We have errors not only in the qubits, but also in the measurement of the syndrome. But it is very interesting that, well, 4.5% is not very far away from 11%. So it's very, very successful. I mean, we still have in the same order of magnitude. It's a very good news from the practical point of view. From the theoretical point of view, this is even more remarkable, because people had done the same analysis before for the Kita F code. They have studied the Kita F code under qubit errors and measurement errors. And the threshold is below, is 2.9, around 2.9, let's say 3%. So it's less than this. Remember that before it was equal, 11% for both Kita-F and toric code. Now, when you brought about more general errors, qubit errors and measurement errors, it so happens that the color codes are more protected. 4.5%. Now, this is very good news in practice, and theoretically, it is a mystery again. It's a mystery. Why they are different? Physically, I can tell you why. Well, at least something qualitatively. In the previous case, both transition points, they were second order phase transition, and there was a self-duality property that fixes the same value. But here they are different because one is second order and the other is first order. That's as much as I can tell. But why is one above the other, or what type of bound they could satisfy? This is unknown. This is something that is a mystery. I mean, these are numerical simulations, and actually I must tell you that here it says revisit because we have revisited the study of this Japanese team with our methods. We use different methods than them, and we have checked that this 3% with our methods we have reproduced it. So we have reproduced this, which is new, and this one that was from the Japanese group with our methods. This method that I told you before with the squareness. And with this I am done because. So the question is, are topological color codes stable towards bit flip and measurement error? And the answer is yes, and actually better than Kita-F code. So I finished. I'm sorry, I ran out of time. This is again my collaborators. And the references, you can find this is in this paper on tricolor lattice gate theory related to fault-tolerant topological color codes. These are more references regarding these properties of these codes and statistical mappings. And I think we have proved that fault-tolerant quantum computation can be done efficiently because the error threshold is of the order of %, while with non-topological, I mean standard quantum error correction, you go to 10 to the minus 5 to the minus 6. So fault-tolerant quantum computation can be implemented efficiently one day by means of these topological quantum ideas. So let's hope for the best. So I think the best is yet to come. Let's wait for the future. And for the moment, many thanks for your attention. Thank you.
So, am I correct? The storyline is detecting something related to the glass system?
No, glasses. No. Well, no. This random Bourne model is introduced in order to study glassy transition, right, in arbitrary dimension. Now, this Nishimori line is a line that Nishimori introduced. Is a line in which an enhanced symmetry of the system appears and allows you to obtain analytical relationships between observables in the theory. To have analytical result in this random statistical model is very difficult. I mean,
so there is no glass in it?
No. And especially along the Nishimori line, there's nothing. There's nothing.
Same question. Go to the order phase. When you have this blue Nishimori line, how do you calculate now with blue? What is the characteristic for this shape? You are in one phase, what we call the order phase. How do you calculate now this blue line within an order phase?
That line, the Nishimori line, is an exact line. So
defined by what?
It's defined by the condition that I can compute the probability of finding a guessed error correction line, the one that I do, with respect to a statistical model. So the statistical model is an auxiliary model that I construct in the plane P for the disorder, and T is the temperature, but this temperature is an auxiliary, a fictitious temperature. It's not the temperature of your system, of your quantum system, no. It is a temperature of a statistical mechanical model that you use in order to calculate this probability of finding the real error plus a deviation, a circle. This is a topological deformation. And this can be related to a partition function of a random Ising model, random Born Ising model. And the random depends on T, this T, and this P. P goes into the quenched variables. So now, in doing this mapping, I have to impose that this relationship holds. So this is a definition. So this corresponds, so this is a line. So I can, this is a line that goes like here. Now, I know that I am, in the quantum computation case, I am along this line because of this constraint. Now, what I do is I use the phase diagram of this model. I start computing it until I hit. And this is the multi-critical point. And this defines my threshold. So, in other words, if you can compute this point directly along the Nishimori line, that's fine. But we don't know how to do that. Right?
Okay, I also have a question on this phase diagram. Actually, I understood that there are two phases, right? For ferromagnet and paramagnet. Right? So, you have this pattern Nishimori line. So, what about the difference between a ferromagnet inside and outside?
Here and here?
No, the other way around. Here and here.
Here and here?
No. Say this and this.
No, there is no difference.
There is
no difference. There is no difference. So, say this is a dash line that corresponds to my quantum computation, right? Nishimori line didn't introduce, was not introduced by Nishimori because of quantum computation. It was done much earlier in the context of a glassy system, random spin system. It was introduced because in this line there is a supersymmetry. And this supersymmetry allows you to obtain relationship between observables, like for instance the glass or the parameter, and they are exact. And this is what Nishimori realized, and it's something very interesting because it's the only thing that can be done analytically in this type of system. Now, miraculously, it so happens that this line is precisely the line in which this quantum computation happens to take place. You use this statistical model as your model for doing the error correction. But it's something I cannot go deeper because I don't know why is it.